Today we begin Unit 2 on dilations, similarity, and we'll introduce slope in this unit as well. Welcome to Lesson 1, Sketchy Dilations, exploring dilations and similarity. Today we're just going to get our feet wet with dilations and similarity as we understand that figures are scaled copies of one another. If that's the case, then they're similar figures. In this unit, we're going to start with the guided notes so that you have an idea of what to anticipate when we move to the lesson slides. We're on page 63 for these guided notes. In this first lesson, I want you to make sure that you know what it means for two figures to be similar. We'll explore what similar figures are in the second half of these notes. But we're going to start with an important word in this unit, a dilation. A dilation is a new kind of transformation. We've talked about rigid transformations, rotations, reflections, and translations. But this new kind of transformation is a dilation in which each point on a figure moves along a line and changes its distance from a fixed point. I think that's going to make a little more sense if we do a figure with this in mind. So I've cheated and started with triangle ABC here, and I've made a fixed point over here. We'll give that fixed point a name in a few minutes. But let's do this transformation. Each point on this figure is going to move along a line and change its distance from a fixed point. Okay, so I am going to transform this point A, moving from this fixed point through that point on the figure, and I'm going to put my new point A here. I'll call it A prime. For point B, again, I'm going to start at this fixed point, pass through point B, move along a line. That's going to be my B prime. And same with this one. I have these measured a certain way. I'll explain that more in a moment. Again, I'm starting at the fixed point, passing through this vertex, and that's going to be my new point C prime. Let me draw that dilated figure. And you can see that it's the same shape as my original triangle, but it's a different size. This one's bigger. Dilations might make a figure larger or it might make a figure smaller. So that was the transformation. That's a dilation. A prime, B prime, C prime is a dilation of triangle ABC. It's a transformation in which each of the points on a figure moves along a line and changes its distance from a fixed point. Let's talk some more about some facts about that fixed point. The fixed point has a name. It's called the center of dilation. I'm sorry, the center of, dilation. The fixed point is the, new word, center of dilation. You're used to saying center of rotation, and so am I. Center of dilation. And you saw me measure a moment ago. All of the original distances are multiplied by the same scale factor. All the original distances are multiplied by the same scale factor. We'll talk more about scale factors in the lessons to come. It's just going to be a number that we multiply by in this unit. So maybe you noticed me doing this. I'm going to draw some little dashed lines. So here's my center of dilation. And that scale factor for these two figures is 2, because I'm doubling the distance from the center of dilation to the original vertex. In this case, with point A, that distance is 1. And I just doubled it. I multiplied that distance by 2, and that's the distance between the center of dilation and my image. Okay. So if this distance is 1, the distance to the image is double that. Draw a little dotted line here. For point B, if the distance from the center of dilation to B is 2, the distance to the image is double that, or in this case, 4. And for C, if the distance is 1.5 to the pre-image, then the distance to the image is double that. So that scale factor was 2. I just multiplied all those original distances by 2. So that's our center of dilation. And I also want you to notice that if I were to line up all of these corresponding vertices, they would intersect at one point, that center of dilation. I think it's a little silly to make some non-examples, but we'll do it. Let's do a triangle, and a triangle that's clearly not the same shape. Those aren't the same shape. It doesn't matter that they're not the same size. Dilations can be larger or smaller. But I'm going to show you how I know for sure that these are not similar. I'm going to try and line up the corresponding vertices, if I can figure out which ones are corresponding. And I know these are not going to intersect at one center of dilation. Ugh. Let's see. Gosh, I wouldn't even know which ones to match up. Let me try these. You can see that as I'm matching up vertices, well, I don't even know if these were two good examples. I could go the other direction and see if they match up, but I'm pretty sure they're not going to. One more. No, it looks like 2 lines intersect here and 2 lines intersect there. So those aren't an example of a dilation. A dilation should neatly line up all the corresponding vertices and meet at the center of dilation. All right, so we'll be talking a lot about dilations. And dilations result in similar figures. Let's go ahead and define similar figures. Two figures are similar if one can fit exactly over the other, after rigid transformations, and I'm not done yet. So far, what I've described is congruent figures. But after rigid transformations and dilations, that might give me a similar figure. So these two figures are similar if one can fit exactly over the other. So if I lined B up right with B, that angle would fit in perfectly from the red triangle to the green triangle. And then if I blew it up, I enlarged it, it would eventually fit perfectly into the image. So I just want to make the point that other rigid transformations might happen first, but then one needs to be able to fit into another. So I'm going to do one rigid transformation and then one dilation to show that I've got two similar figures. This is going to be a little bit sloppy. Bear with me, I don't have transparent paper. I'm going to start by just rotating triangle ABC 90 degrees. I'm just freehanding this. So this is still B. I rotated on point B. This is going to be A. I'll make it A prime. And C rotated down to here. So I just rotated this around, not perfectly, obviously. And now I'm going to enlarge it. I'm going to dilate it. So let's see what I want to dilate by. Looks like that's about 2 units to point A. I'm going to go off the page a bit. I'm going to double it again. So this is going to be my A double prime. From the center of dilation to B is 1 unit. I'm going to double that to put that here. And to point C, originally that's, oh gosh, 2.5. I'm going to double that to be 5. That's going to be C prime. All right, so I lost B prime in there a little bit. But I'm just going to connect these all up. So you can see that I started with a rigid transformation. I did a rotation. And then I did that dilation. So if I had done this more precisely, we could see it a little better. But the shape of all 3 of these triangles actually should be the same. They all have the same angle measures actually, but they're just different sizes. So these are similar. One can fit exactly inside the other after a rigid transformation and a dilation. I might throw an enlargement or a reduction in there at the end. Some quick facts and characteristics about that. If ABC is rotated around point B, let's just describe what I did. If triangle ABC is rotated around point B, and then dilated, with center point, we'll call this O. Then it will fit exactly over triangle D, A prime, B prime, C prime, or A double prime, C double prime, B double prime. Forgot to mark the double prime. And that means that they're similar. So they have to be dilations. So if I had this figure here, and then I had a figure that looked a little stretched out of whack, the proportions just aren't the same here. So these would not be similar figures. Again, if I lined up the corresponding vertices, they wouldn't meet at a center of dilation. So just to summarize what we're saying here, how can we check to see if 2 figures are similar? Well, if you can make them congruent through transformations and dilations. I'll say through rigid transformations. And shrinking or enlarging, also known as dilations. Okay, so that's the grueling part. Let's have some fun with dilations and similar figures as we move to the first lesson in Desmos. Okay, I'm in lesson 1 on Desmos. I'm going to move through these slides, but I encourage you to try this on your own as well, just to get a feel for it on your own. So I'm on this first slide to warm up, and we're asked to try out the stretching machines below and play with each until you can describe to a partner how one changes your drawings. Now keep dilations and similar figures in mind. We'll try machine number 1. Now imagine that in the upper left, that point that's not moving is the center of dilation. My gray dot is going to be my original image, and I can see that there's another dot that's moving on the far right that looks like it's about twice as far from my from the fixed dot as the gray dot is. So as I bring the gray dot to, let's say that's about a centimeter away from the fixed dot, the other open circle is twice the distance away. That's what it looks like happens no matter where I move my gray dot. Let me try machine number 2. All right, that fixed dot is my center of rotation. And this time it looks like my gray dot is, still between the two open circles. But it doesn't look like that other open circle that moves is twice the distance anymore. It's a little less than twice the distance. Let's try machine number 3. There's my fixed dot in the lower left. That's my center of rotation. And this time, as I move my gray dot, the gray dot is twice the distance from the other open circle. So this time the gray dot's not between anymore. The other open circle is closer to my center of rotation than the gray dot. Let me try the 4th one. Oh, and this one's very interesting. It looks like the center of rotation is actually a pivot point this time. And the other open circle is on the other side of that center of rotation. It looks like it's about half the distance away as the gray dot is on the opposite side. All right, so using the word center of rotation again, let's move on to the next slide. And we're asked to trace this shape and ask, how would the image be different if point A were closer to the triangle? All right, I am going to use my mouse to trace shape A. Trace the triangle. Point A is my center of dilation. I hope I've been saying dilation. And what I'm about to trace is my pre-image. And what you see in pink down there is the image. It's a lot more fun if you do this on your own. There we go. So there's my image and my pre-image. How would the image be different if point A were closer to the triangle? Well, I think the image would be closer to the triangle, closer to the pre-image, but it would stay the same size. Let's go ahead and see if that's correct. So it says a dilation is a new type of transformation that you've been exploring in this activity. If we move point A, let's ask ourselves, does moving point A, that center of rotation, center of dilation, change the size of the image, the location of the image, or both? Well, let's first think about the size. Does it change the size of that image I created? Nope, doesn't look like it. Does it change the location? Yes, it does. So I will say it doesn't change the size, but it just does change the location. So I can say no matter where I put point A, the point in the image is about twice the distance as the point in the pre-image. So this point on the image is about twice as far from A as this corresponding point on the pre-image. Now, those stretching machines that we were using in this activity create dilations that we talked about earlier. Same shape, but maybe not the same size. Let's choose an image that could not have been created by tracing an image with that stretching machine. And if we look closely at these, I'm going to look closely at this first one, and it looks like the rectangle for the dotted line and the rectangle with the solid red are the same size, the same shape, but not the same size. If I look closely at this one, first of all, I can tell that rectangle C is not the same shape as square B. And as I'm looking at these lines, I want you to notice that the lines connecting that center of dilation, B and C, that line's not straight. So that's not going to make a dilation. If we look closely at this one, we can see that one of these is a hexagon and one of these is a pentagon. That's not going to work. And in this figure, I've got a trapezoid for the red and a rectangle for the dotted line here with rectangle B. So there's 3 images here that might not be dilations. I'm going to choose this one and just say figure B is a pentagon and figure C is a hexagon. So we also talked about similar figures. 2 figures are similar if one can fit exactly over the other after rigid transformations and dilations. So dilations make figures that are scaled copies of the pre-image. We also call these scaled copies similar figures. What do you think it means for 2 figures to be similar? I'm going to say same shape, but maybe not the same size. So let me just take a look at these, and just real loosely, we're going to click on the figures that you think are similar to figure A. Which ones look like they're the same shape, but maybe they're not the same size? As I'm looking at this figure, this one looks like it's just a bigger version of A. I'm going to click on that one. This one, the proportions seem off. This one, I know I need to have at least a right angle here. There's no right angle in this one. This one over here looks like I did a reflection. I flipped it over and then shrunk it and translated it too. But it's the same proportions. I'm going to say that one's correct as well. And we'll do one more like that. Again, we're going to click on the figures that you think are similar to figure A. Okay, this one's got a right angle again, and one of the legs of the right angle is a little shorter than the other one. Let's see if I see any other figures that look like they're about the same shape. I'm going to say no to this one on the top because it doesn't have a right angle. This one just looks too long. And right now, that's all we're basing our thinking on, is kind of what looks right. We'll get more concrete later in the unit. The one right below it looks like it just shrunk down a little bit. And I think this one looks like it was rotated and then enlarged. If I took A and rotated it about 180 degrees and spun it around and then enlarged it, I think this one would be correct as well. So in today's lesson, we wanted you to understand that figures that are scaled copies of one another are called similar figures.